All right, guys, enjoy your lecture.
Better wait a couple of minutes. Start at 5 past.
See you. Enjoy.
Oh. What's going to happen next term? We're going to be closed down. Are we going to die? Let's be optimistic. Right. The holiday break is coming up. Take a break. You need a few days change of scenery. But after Christmas, maybe after New Year, start thinking a little bit about your courses and your project. Read through some notes. Have a look at past papers. You should be able to answer the exam questions now on distance classifiers. So anything and everything to do with distance classifiers should be in the brain. And you should also be able to answer all exam questions on analog neural networks. Their training, their response, their structure, their properties. And today we're going to start on a part 3, I guess it is, of the course, which is going to be digital models of a neuron. Now this is interesting. So let's get started. Yes, might as well find some pens that write. Let's try getting off the top of that stupid thing. Why is that smudged? That's better. There's a splodge on the screen somewhere. Oh, well, you have to restore the images in your own neural networks. Right, digital neural networks. We started off with that machine, which was Princeton around about 1950. That was a physical hardware model of one single neuron. And the weights were controlled by motors driving variable resistors, and the whole thing whirred away. It was operating off 16 by 24 pixel images, 384 motors in there, all using Hebbian learning, changing the weights. If the output got better, stick with it. If it got worse, go back to where it was. It must have been a fantastic thing that was created there, and they just sat back and let it hum away. Only one problem with it, it didn't work. They couldn't get any sensible results out of it. And of course, what they weren't, God, missing you.
YouTube.
Right, so that thing didn't work, and they didn't really understand linear inseparability, which you guys all understand what linear inseparability is. And they had no chance of trying to explore it in 384 dimensions. If they had tried to explore it in 2 dimensions, they might have got some clues, but I guess they weren't particularly bright in Princeton in those days. So they introduced a fiddle factor on this machine. So let's go away from there and get a schematic of the machine. There is your single neuron. Here are your weights. That's W, and this would be weight 1 down to weight 384. That's a big machine. all going into a summer and a threshold coming out. And we have our input picture here, where each pixel was an input, and this was 16 by 24. That was the resolution they chose. So the input I is 384 dimensions. And that was connected to all the weights. They tried to find the weights, tried to get the output they desired for character recognition. It was used for recognizing a letter. And it just went on and didn't work. They came up with an idea. I don't know where the idea came from. They introduced an association layer. Now, if you look at very old papers on analog neural networks, you will see this association layer at the front end. It seems to have disappeared in recent times because they've understood that these single neurons will not solve problems. They go to multi-layers, and the multi-layer can learn to transform. But they introduced a series of inputs, as many as they liked. These would be driving the inputs here, and these would be taking a series of inputs, pixel inputs from the front. And this was the association layer. Association layer associates inputs. Now, the data they were using were black-white images, noughts and ones. You know from the Phi machine that it is difficult to do mathematical transforms of noughts and ones, because if you square the inputs, 0 and 1, you end up with 0 and 1. If you start multiplying the individual elements together to get a supposedly higher order transform, in binary, it has the habit of going to 0, because any one 0 in the multiplication, you've got 0. So they were trying to associate inputs, one input with the other, or one input without the other, and so on. And it was a primitive form of logic. And of course, in 1950, logic as microcircuits didn't exist, because Schottky had only just got the microcircuit going 3 years earlier in Bell Labs. And logic in those days was switching relays. And you can build up AND and OR gates by having a series of switches, which was basically the forerunner of diode logic, if you've looked into the circuits. So this layer was essentially logic. So that was the scheme that got the McCulloch and Pitts model working, and they got some results from it. In fact, they invented the Phi machine without realizing they'd done so. So that was the background from the original analog system. If I now go back to the neuron, which is providing the inspiration for our modeling, engineers and medical people don't agree on very much, but we do agree that the inputs and the outputs fire. And so what we've got here is inputs which have waveforms, complex waveforms, which can be simplified as being dormant or firing like billiard. And that's true on all the inputs. It's also true on the output, and that's distributed elsewhere. If we have two states on the inputs and the outputs, it's a binary machine. And so what goes on in the middle of that neuron, what would be a candidate model to relate binary inputs with a binary output? What would be a candidate model? I've got noughts and ones going on the input, and I want a 1 or a 0 coming on the output. Does that sound familiar, like a truth table? Yeah. And what does a truth table implement? A logic function. So an approximation of that model would be a logic function. So directly from a neuron, we have a waveform like this, a voltage against time, and it might be a black pen. It might be
toddling around, then all of a sudden it will start firing, it's dormant, firing, and so on. And so we can code that as a 0, a 1, a 0, and a 1. So we can implement that model with a logic function, combinational. So there's sort of a link with the natural system to get our logic function from natural neurons. Right, now I want to introduce a completely non-neural network process, but it does exactly what the neuron does. It was a method for pattern recognition. It's called the Browning and Bledsoe method. It was a pattern recognition method, and it was about 1959, so it's quite an old method. And if we take a pattern, which is a picture, and if I put on that array a character, the letter T, if I were to take one pixel, how many decisions can I make on that one pixel? Simple question. 2, 0 or 1. So a single pixel, 2 decisions. And that is going to be 0 or 1. Or in the case of an image, it's going to be a pixel that is black or a pixel that is got a cross in it. Now, if I'm trying to make a decision on characters, there's 26 of them, I'm looking at one pixel, I can't make 26 decisions. I can only make 2 decisions. It's not enough. So, if one pixel won't give me enough range of decisions, what do you suggest we do?
Get more pixels.
Get more pixels. 2 pixels. And how many decisions can I make on 2 pixels?
4.
4. It can be 0, 0, 0, 1, 1, 0, and 1, 1. Those are the data that can occur on 2 pixels. And if I want to make a yes, no, a binary decision on those, there are going to be 4 ways of doing it. I can separate 0, 0 from the rest. I can separate 0, 1 from the rest, which will be 0, 0, 1, 0, 1, 1. And you can work out all 4 combinations. That was going to be a 1, 3 separation. But I can also separate in a different way. Any suggestions? So instead of 1, 3, 2, 2. So I could have a separation which might be 0, 0, 1, 1 from 0, 1, 1, 0, which happens to be the XOR function. And if I were to take 3 pixels, what's the space in 3 pixels for decision making? How many patterns?
9.
Ah, binary fool. 8. If I was to take 4,
16.
16. So the scope, the range of decisions I can make is increasing. If I go to 8 pixels,
200.
256. Now, how many ways of separating groups within 256 values is pretty huge. So we're now creating a huge space for decision making. We can change the way we extract information, and we've got more ranges of possibilities of making a decision. And if I were to take 10 pixels, 1,024 states, which can be partitioned. And you can certainly partition 1,000 states into 26 classes. You could, in the limit, separate it into 1,000 classes if you had one pattern per class. So we've now got the potential for multiple decision making. And this is what Browning and Bledsoe got cottoned on to. And they took an image and they called it the n-tuple method. Because they are taking n pixels. And if I were to take 3 tuple, one way of sampling is row by row. And that is easy to follow, so I will use that. But it could be column by column. It could be random 3 pixels from the image. So again, we've got ways of extracting the information. And this is referred to as the mapping. So if we now take a problem, let's come down here. Let's take character recognition, the letter T. Let's take a perfectly good printed T. Let's take another T with a shorter vertical. Okay. And let's take a T with a sloping top. Now, if you were looking at those, I guess you as a human would perceive those all to be T's. They're not X's or J's or whatever. Now, if I reduce those to my 3x3 resolution, and in exams, 3x3 examples might be required. In practice, it's going to be 16x16 or much higher resolution, but the principle can be demonstrated with a 3x3. If I put these on the array, the data I'm going to get is this T would be that one. This T would be a shorter vertical. And the final T will be at this low resolution, a sloping top with that. So that's the data, 3x3 encoding those real characters. They are different, but they are all the same class of pattern, the letter T. And if we look at row by row samples taking a 3 tuple, if it's a letter T, we can have 1, 1, 1, black, 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 depends how you encode it on the top row. Yes, we've got it again, but we can also have 1, 1, 0. It's an allowable state in the top row for the letter T. Middle row, 0, 1, 0, or 0, 1, 1. Bottom row, 0, 1, 0, or 0, 0, 0. And what Browning and Bledsoe did, they produced a method, a software method. 1959 machines were pretty ropey, but the idea was to store allowable n-tuple states for a training set. And then when you have an unknown pattern come along, you correlate the n-tuples with the states that are allowed for every class in the system. And you get a score. If it correlates, you increment a counter. If it doesn't, you keep it the same. So that was the idea behind Browning and Bledsoe's method. So let's take that data. And that's my training data. And let's have the samples. And the states. Right, the samples. Sample is 1 is the top row, 2 is the middle row, and 3 is the bottom row. So I can build up a table for the T class. Right. Oh, you stupid machine, stop. Made your mind up. Right. For pattern sample 1, the top row 111, let's call it 7, which is 111. Easy to write decimal. For the second training pattern, yes, I'm expecting 7. But the third training pattern, I'm expecting 6. Yep, with me? For the second sample, which is the middle row, I'm expecting 2. And 2 again. We're not taking into account the frequency of occurrence. It's the simplest possible model. If we take into account the frequency, yes, that's interesting, but we're not there yet. Just has it occurred in the top row or has it not? That's all that's necessary. And for the final pattern, it is going to be 3. And for the third sample, the third row in this case, it is going to be 2, 0, and 2. So those would be the allowable states for the letter T. Now, if I was sampling column by column and taking the top as the most significant bit and the bottom as the least significant bit, what states would I have for the columns? What's in the first pattern column?
1, no,
In decimal?
8.
4.
4, yeah.
And the middle one?
8. 1 on.
4. 1, 0, 0. Third pattern?
Oh, third pattern.
1, 0, 0.
Yeah.
So for the different mapping, we're getting different states. In this case, it's consistent. For the middle row, column by column sampling. 7, 7 and 6 repeats. Forget about repeats. And the right-hand side. One, 0, 0, 4. Same again. 0, 1, 0. You can do binary numbers, can't you? Please. You can work out binary numbers. Yes? You're just tired. Had a party up over the weekend, eh? Okay, so the mapping will change the allowable states. And I can test on other patterns. So let's have a test pattern. Let's take in another T-like structure. Let's have that's a T, a sort of stylish T with a sort of wedgy top, something like that. You might perceive that as a hammer, but in terms of character recognition, that's a particular font of a T. Right. We'll go back to the row by row sampling because that's what we've got these states for. What is the state in the test pattern in the top row? 7. Is 7 an allowable state? Sample 1.
Yes.
Yes. Middle row. 3. Is it allowable?
Yeah.
Yes. Bottom row.
2.
Is it allowable?
Yes.
3 out of 3 for the T's net. Hey, it's not a training pattern. The method generalizes that property that we do need. It's generalizing, it's recognizing patterns which are similar, but not exactly the same. Now let's test it on another character. We're limited at this resolution, but let's have pattern If I told you that was a character, what character would you say it was? X, or at least we can character. Right, top state. 5, is it an allowable state?
No.
Middle row,
2.
allowable, yes. Bottom row, 5. No, so we get a score of 1 out of 3. Now, an output threshold, set the threshold at 3 out of 3. It's not recognizing it as a T, whereas the previous one would do. Let's put in another pattern. What character would you say that is?
L.
L. Right. Correlate with the first samples. 4, no. Middle 4, no. Bottom 7, no. 0 out of 3.
No, 7 words.
Third sample. 1, 2, 3. Third sample, 2, no. 0, no. 7's not there. 0 out of 3. And that was their method, and it was used on character recognition. It worked pretty well. They used handwriting rather than printed characters, which is harder. They got about 80% recognition on 26 characters. So what they would have is not just one set of states for the letter T, they'd have a set of states for the letter A, a different set for B, C, D, right the way through to Z or Z. 26 states. And they would have those tables. Then a test pattern comes along, and you would test it against all the character lists and get a response. How does L compare with the A class, B, C, D, E, right the way through? Look for the highest response, and that's the classification of the unknown pattern.
Include the lowercase letters as well.
Don't complicate it. Keep it simple. Keep it simple. They chose handwriting, which is tricky. Had they chosen a very careful print and type print, it would most probably work much better. They got about 80% success. Now, 80% success is certainly better than chance on 26 classes. 26 classes, pure chance guessing, you'd expect 4%. So there's something in this method. But unfortunately, like most of these applications, it wasn't good enough. Because if you take a postcode, which has no context, and you've got characters and letters in the postcode, you've got 6 characters which have to be recognized individually. The probability by chance of getting the 6 characters correct is pretty low. You can work out what's the chances of getting the first one correct. It's going to be 1 in 36 if you have 10 characters and 10 numbers and 26 characters. Getting 2 is going to be 36 squared. So by chance, it's pretty low. But 80% was interesting. It wasn't good enough. And also the problem then, remember this is 1959. Computers were driven by steam. They were slow. These tables were quite big. Scale this up. Instead of having 3 bits, we would have 8 bits, typical value of n. 8 bits is possibly 256 allowable states in each case. And when testing, you've got to manually search these tables for a match. The A class, all the states, and the number of samples, 18 by 24, 32, n equals 8, you would have possibly 256 maximum in each entry. A lot of searching and checking. So clearly wasn't working in real time. Now, where does this tie in with logic? If I wanted to test the membership of a interval with a given sample, my input is 1, 0, 0. I've got to say 7, no, it's not 4. 6, no, it's not 4. We've got no correlation. But if I were to take a logic function with 3 inputs, let's call them A, B, C, A, B, C, and the output is F. And if I have on A, B, C, this is a function here, 7 and 6. The function I want is 1 and 1, all the else 0. What is the logic function to detect a 7 and a 6 in terms of ABC?
A and B.
Don't minimize it.
Oh.
Go on, you can tell me.
You can
ABC.
A, B,
A and B and C,
or A, B,
or A and B
not C.
and not C. That is the logic function which will determine membership of the allowable states. And of course, it's instant. It's not, it's a parallel process. You put the input, if it correlates, if it's an allowable state, the output is 1. If it's not allowable, the output is not. Right, that's interesting. In fact, that's bloody interesting. Because what we have potentially discovered now is that in training this system, let's start off with the first pattern, go back, suppose I just had the 7, the function would be f equals A and B and C. If I now get the 6 coming along, the training requires me to recognize ABC equals 1, 1, 0. I don't want to lose the previous training. I was going to use the word add, but I need an additional term, which is going to be A, B, and not C, 6. And in changing that function, I do not lose the response to the first train pattern. And this gives the possibility of single pass training. You don't get this property with a McCulloch-Pitts neuron. You change the weights, you might have got a previous pattern that was correct wrong. But with the logic system, you are retaining the previous ones. So that's overcome a major objection to the McCulloch-Pitts. The training, instead of taking hours, days, months, and maybe not concluding, the training is a single pass. And if you're building this up in hardware, the training can be at the microsecond speed. Brilliant. Okay, now the generalization. The single logic function cannot generalize. This function here will only ever respond to what it's been taught, trained on. 7, A, B, C equals 1, 1, 1, or 6, A, B, C equals 1, 1, 0. Okay, can't respond to any others. So where does the generalization come from? It comes about because we have a choice of patterns on the first sample. We have a different set of choices on the second pattern. We have a different set of choices on the third pattern. Now, to get a correlation of 1, 1, 1 for this particular training set, we have to have either a 7 or a 6, or a 2 or a 3, or a 2 or a 0. We have to have allowable states at each sampling site, but they do not have to occur in the same training pattern. So we are, if you like, giving alternatives to each sample for responses. So if I took this pattern, go back to the idea of having logic functions, let's go back to my training patterns. I think those were the ones. Those are patterns 1, 2, and 3. Can you work out a pattern, the letter T, that will give a response of 3 out of 3, which is not one of those training patterns. And just give me the decimal of the 3 bits. Go on.
630.
630. Right, state 6, yes. State 3, yes. 0, yes. Yes, that will give a response. Now, the resolution is 3 by 3. It is trivially small. That is being interpreted as a letter T. It doesn't really look like it, because it's not much detail, but I guess it has some T-likeness about it. Give us another one.
720.
7. Another one.
20.
2. That's the training pattern. Give us another one.
730.
730. Yep.
622.
6, 2, 2. Yes. T-like. Give us another one.
620.
620. Have we got that one? No, we haven't. Maybe not. Keep going. One more.
730.
7, 3. Got that one.
75.
5. 5. Okay, let's do it systematically. Including the training patterns, we can have 722, which is that one. We can have 720. Have I got 720?
732. Yeah, that's the last one.
No. No, that's the one missing. 7.
32. That's the second one.
Oh, it's just train pattern. Thank you. Good. Right, so we've gone there. Now 732.
And 632.
Hang on, let's go through them. 732. Have we got 732?
No.
Yes, no.
No.
732, that's the one, yes?
That's 730.
I want 732.
No.
Yeah,
Yeah. And 632.
632. 632.
The training plan.
So training pattern. I think that's the lot. Why is it the lot? Mathematically, we have a choice of 2 at each sampling state. So we have a choice of 2 for the first one, times 2 for the second one is a choice of 4 in the first 2, times 2 for the third one, 8. 8 patterns. So that structure is recognizing 5 patterns that weren't in the training set. It's generalizing. Brilliant. So that was the idea behind the Browning and Bledsoe method. And if we move forward in time to the 1960s, to 72. Yes, I was alive in those days. In fact, I was a PhD student in the early 70s. I just remember those days. Right. The structure we want and we're summing and we're applying a threshold. And we are taking a 3 by 3 image, and if we are connecting it up row by row, There's a connection. So what we've got here is the input, let's say n pixels. This is the mapping. The n-tuple size is the number of pixels being grouped together, so this is the n-tuple. These are logic functions. And the summation and the threshold you should recognize. Right, again going back in history to 1970, logic was about, in those days you could buy logic gates, but they were expensive. You had to, if you wanted to change a function, you had to get your soldering iron out and reconnect the things and whatever. And it was that time that somebody came up with the idea, and I'm sure you would have that idea, of what would be an ideal hardware structure for the logic functions. For all your logic design, how would you design logic today? How do you implement it? Proms? No, it's not a party at the end of term. Or if you're classically minded, a constant in London. Programmable logic. Yeah. And what is programmable logic? Well, it's these beasts here. If we can take a programmable device, we can change electronically the function without getting your soldering iron out. And the idea, and this is part of the research group I was working with at the time, we came up with the idea of if we take 8 DFFs and a 3 to 8 decoder with a little bit more logic, we could actually store the truth table. And this really was the first idea of programmable logic. It was an 8-bit programmable device. We scaled it up to 16 bits before we built it. And the structure was, I'll do the 8-bit one. 3 inputs, you have a decoder there, and you have 8, 1, 2, 3, 4, 5, 6, 7, 8 DFFs. Decoder. And we have an OR gate on the output, there's a function coming out, there's A, B, C going in. That very simple structure. And we designed it, a guy called Ray Glover, who was a colleague of mine, actually did the chip design. And the chip design in those days was to start with a whiteboard and put black tape on it. You had to understand the electronics and the chemical processes to put down the masks to etch the material to create the silicon. No computer-aided design in those days. And we called this device a SLAM. How are I doing for time? We've got 10 minutes left. And that stood for Stored Logic Adaptive Microcircuit. We thought it was a snazzy name. It was the biggest mistake me and my colleagues ever made in our lives. Because we got the name wrong. What should it have been? Stored Logic Adaptive Microcircuit. Doesn't matter. That's history. We should have called the damn thing a RAM. It was a random access memory. And had we done that and got a patent on the idea and charged a billionth of a penny per bit of storage, I would have Paul Zuckerberg cleaning my house for me. Indeed, shining my shoes. And it was basically the first idea of a random access memory. We called it a programmable logic device, which is what we wanted. Never thought it would be used for computing. I mean, you had little carbon ferrules, beads, to store your ones and noughts through magnetism in those days. So we made a big mistake there, and I've suffered ever since because I've been teaching people like you for the last 50 years. So we built this damn thing, It was made by Plessey, and we had about 3,000 made, and we kept about 1,500 of them and sold the others off as we're interested. 1, 2 people were interested. 6 months later, a company called Fairchild came along with a 64-bit memory, which was 8 times bigger than ours, and it was 4 times if you go to the 16th version. And that was the first commercial random access memory. Even then, people didn't think it's not going to catch on, this idea of electronic memory. We've got to have our magnetic memories and whatever. And of course, what have you got now? You've got a memory stick in your pocket. Anybody got a memory stick? How big is it?
128 gigabytes.
128 gigabytes. So this is going to be 8 bits. And you have 128 gigabytes. How many bits in 128 gigabytes? So obviously 128 times a giga is 10 to the 9. No, it isn't, it's 2 to the 30. And bytes, what's byte mean? 8 bits times 8. Somebody work that out for me on the calculator just for fun.
Thousand 24 times 2 to the 30.
124.
1024
1024
times 10 to the
times 10 to the
sorry times 2 to the 30.
oh 10 to the 10.
Yeah.
That's not, approximately. Hell of a lot of bits. That's the progress in memory. And what did your memory stick cost you?
25 quid.
Oh, you should. Thought they gave them away these days. And that's the development in memory. So we're going to use programmable memories for our logic functions. So let's now go back, and this will be my last diagram for today. Here is going to be my 3x3 input. Again, 3x3 is a trivial example. Think 512 by 512. You can scale this up enormously. Let's now take 3 logic functions, and I'll draw them as a register, and I'm going to use 3 inputs. So they go into a summer and a threshold. Let's put the addresses on here. We're going to have 1, should have 8 cells in each of them. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's correct. And we're going to have the inputs. So let's now train this system on the patterns I started off with. The first pattern was the T there. And let's write the addresses at the top here so you'll. Naught, 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 1, naught, 1, naught, naught, 1, 1, 1, naught, naught, 1, naught, 1, 1, 1, naught, and 1, 1, 1, 0 to 7. Okay. Input pattern 7. Initially, they're all set to 0. Seven comes in here. We set a 1 there. For the middle pattern, it's going to be 2, and it'll be location 0, 1, 2 is set to 1. And the same is true for the third one. So that's trained on one pattern. Put in the second pattern, which I think was that. 7 and 2 don't change, we've got that, but the third location can be a 2 or a 0, all zeros. And the third pattern was, let's draw it again. That one. The first one is now seeing 6, so location 6 is set to 1. Location 3 is set to 1. And location 2 is set to 1. We've already got that. So those are the ones in the memories. All the other locations will be 0 because they were originally set at 0. There we are. And so that would be the trained memories representing those logic functions. And the key thing to notice about this is we are using 8 bits of memory for each function. 8 threes are 24 bits. And that is fixed. It doesn't matter how many patterns you train this thing on, the memory remains the same amount of memory. It's whether the locations are set to 0 or 1, that's what the changes, and that is where the learning takes place. So, we've got a hardware system, no iterative training. Once you've set the memory for a given input location, it will give the output of 1. Initially, they're set to 0, so you can build up a processor, which we tend to call a discriminator. It's arguable whether these are the neurons or the whole thing is a neuron. It doesn't really matter. It's a learning process, learning structure, which builds up the functions with training, and the training is a single pass. And of course, 24 bits of memory implement a 3x3 pattern recognizer. He's got 128 gigabits of memory. He can set up a pretty big system on his memory stick for learning patterns. And it's quite feasible to scale this up to 4,000 by 4,000 pixels. And the other brilliant feature of this scheme compared with the analog network, we have choice of the mapping. And in nature, all our mappings in our brains are different. The McCulloch-Pitts neuron, everything had to be connected, no choice. This gives us immense flexibility. If a particular problem can't be learnt, change the mapping. And possibly we could use this with you guys. If you can't possibly learn to speak Chinese, if I go in there and change the mapping, that potential mental capacity could be receptive to Chinese. Interesting ideas. Okay, I've run out of time. I can go one more lecture before the break. I'll take this structure, and next Thursday we'll look at some of the parameters, how we can change the behavior of the system by changing the parameters. Now, just a final word. We used to, 3, 4, 5, 6 years ago, we had a scheme with the Brazilian government on Science Without Frontiers, and I had 2 or 3 Brazilian students taking this course. They saw this concept, and they thought it was absolutely amazing. They went home after this very lecture, and they simulated one of these things. They tried it on 5x5 pattern recognition, character recognition problems. They saw how it behaved. It worked at that level. They were so engrossed that they took it back to their university at Rio de Janeiro. They've got a PhD working in this area, and I think one of them is now an assistant professor. So there we are. Could change your life. If you want to have fun tonight, knock up a 5x5 recognizer and see how it behaves. And it's a lot easier to understand than the analog. It's logical. Okay, thanks guys.